Now. Okay, so welcome to the Le Chatelier's Principle online lesson. Thank you for coming. So just a couple of things before we start. I'm going to be asking two types of question today. One of them, mostly, there'll be ones you can just type in the chat. If I do that, can I ask you please to type out your answer, but don't press enter until I say so. Otherwise it kind of like ruins it for everybody else. So like type your answer out, but hold it back and then we can all press enter together and see what we've got. Occasionally towards the end of the lesson, there might be a question or two where you can't type on chat, it's too complicated. If that's the case, just write it on some paper and I won't be able to check your answer, but you can just check it against mine when I unveil it. All right, we ready to go? We all good? Yes, all right, let's do this then. So first things first, the whole of Equilibria is based on Le Chatelier's principle. This is Le Chatelier here, this handsome fellow with an awesome moustache. And he came up with this idea, which we call the Chatelier's principle. Everything's based on that. So can you, in your chat box, without pressing enter yet, can you type in what is Le Chatelier's principle? Then we're going to spend the first like literally 15-20 minutes just making sure we really understand what this principle means, because like I say, this is the linchpin to the module. Let's try and be specific as possible and use all those big fancy words if we can. We are going to go through what they mean later one by one. All right, when you're ready then guys, if you can press enter. Okay, let's see what we got. Give me a second, just to have a bit of a read-see. Yeah, you're definitely on the right track there, Lauren, absolutely right. Excellent. I like the fact, you've said position of equilibrium. We should definitely be mentioning that. Excellent, spot on, Theo. Yeah, I like that, Daisy. Rather than saying the system readjust, which is true, you're definitely not wrong, I would say the position of equilibrium shifts. And we're going to talk about what that means in a sec. Yeah, same there, Jason. Excellent. Definitely all true. But again, I'd replace that word system with position of equilibrium. Yeah, and again, it's not the equilibrium that shifts, it's the position of equilibrium, which is different to the equilibrium itself. Excellent, really good answers there, guys. Here's my answer. So, if a closed system, and we'll go through what that means in a sec, in dynamic equilibrium is subjected to a change, then the position of equilibrium will shift to minimize that change. So there's three terms there which are probably quite new. You might have heard of one or two of them before, but what we're going to do is go through each of those three terms, make sure we really understand them, and then come back to this equilibrium, Le Chatelier's principle, and then make sure we really understand it. So three more terms to go through. We'll go through them one at a time, and then we'll come back and read this again, and then talk about what it actually means. So next question then, what is a closed system? If you can type that into the chat. Obviously the opposite of a closed system would be an open system. What's a closed system? I should say as well with your answers, obviously we're all friends here, right? So if you get a question wrong, definitely nothing wrong with that. We've not even had a lesson on this and it's a tricky topic. So if you don't know something or you're not sure, that's fine. Just, do the best you can, type it in. And even if it's not quite right, or even if it's completely wrong, that ain't a problem. Hello, Sam and Ted, nice to see you. We've just been talking about Le Chatelier's principle. At the moment, we're just typing in what a closed system is. Sorry, Thea, I'm not sure there's much I can do about that. I'll try and talk slowly, that might help a little bit. Sorry guys, my internet just cut out then, just bear with me a second. Bloody internet. Bear with me 2 seconds and I'll be back in a sec. Maybe the internet cut out again. Can you get it back to the lesson screen? I don't know how to use a Mac. No, don't do that. It's in my lesson screen.
Because you've opened up Firefox.
Yeah, it's in Firefox.
It's not here, isn't it?
No, it's in Firefox. There you go. Excellent. Thank you. Sorry about that, guys. Can you hear me again? Is that all good? Excellent. Yeah, sorry about it. It's probably my Wi-Fi being a bit rubbish. Problems with it. Anyway, as we were saying, here's a closed system. If you want to type your answer, then press enter. Excellent. Yeah, all of those answers looking good. Brilliant. Not just mass, it's everything. It's not when nothing can get in or out. Now in reality, it's incredibly hard to make an actual closed system, but we can imagine there is one. So it's when nothing can get in and out. I always imagine it as a sealed, perfectly insulated box, right? So that's one term there. Another term, and this is probably the second most important term, is dynamic equilibrium. So again, in your chat box, what is a dynamic equilibrium? Hiya. So just with your answer, the pressure and temp and all of that doesn't have to remain constant in a closed system. It's just that nothing can get in and out. So you can change things in a closed system. So temperature can change, pressure can change. That's fine. It's just higher. They can't be changed by anything from outside. Yeah. That's okay, Thea, no worries. Okay, do you want to pop your answers in then if you've got one? Excellent. Excellent. You guys have definitely done your independent study. Well done. This is really good. Definitely, Lauren, that's also true for sure. Excellent. Yeah, absolutely right. So it's a reversible reaction. I mean, technically every reaction is technically reversible. But in this one, we have where the forwards rate equals the backwards rate of reaction. So this is not to say that we don't have any reactions happening. It's just that for each forward reaction, you get a backwards reaction. My next question, I think a few of you have already typed this in, which is fantastic. If the forwards rate of reaction equals the backwards rate of reaction, then what will happen to the concentration of the chemicals? You can just quickly type that in, press enter whenever you're ready. I think a few have already done that. Excellent, yeah, fantastic. So that's something to be aware of. When you have a dynamic, the word dynamic means things are happening, but the equilibrium means that they cancel out. So I always imagine it's like me, like this would ever happen, me being on a treadmill, I'm running forwards, but the treadmill's going backwards. And so the effects cancel out. It's not like I'm standing still. Okay, excellent. So just one more keyword to go, and then we can come back to the Chatelier's principle and talk about what it means. And this is by far the most important one. So this is the position of equilibrium. So what this does, I'll just give a bit of a intro to it. This tells you about the rate of the forwards reaction compared to the rate of the backwards reaction. And I always imagine it as an imaginary line on this equilibrium sign. So if your forwards rate equals your backwards rate, and we have a dynamic equilibrium, I always imagine we have this imaginary line right in the middle of the equilibrium sign. Now, when you're doing this in an exam, you can just do it with your finger. Just pick your finger up and place it on the equilibrium sign. And when you do your exams in, next summer, hopefully next summer, I often watch through the windows for the first bit of the sports hall, just to kind of see how people are doing. And it's quite interesting if an equilibrium question comes up quite soon, because I see like 250 students pick up their finger and put it on the page. So it is worth doing. People do find it useful. So that's what we would do to show the position of equilibrium being in the middle. That's where the forwards rate equals the backwards rate. But my question to you, if the position of equilibrium, and again, a bit of repetition from earlier, if the position of equilibrium lies in the middle and the forwards rate equals the backwards rate, what would this do to the concentrations of A, B, C, and D? You can type the answer in now, please. And just whenever you're ready, press enter. Excellent, Jason. Yeah. Yeah, so there's two different answers here. I'm just going to type them out. So one of the answers was the conchs remain unchanged. The other one was they have the same conch. Or let me just scroll back. Yeah, they would all have the same conch. Now, this first one is correct. The concentrations remain unchanged. Now, I think when the second one, they have the same conch, I think he was meaning to say this first sentence, but actually that means something different. So if you say the concentration remains unchanged, what you're saying is whatever the conchs are to begin with, they stay like that. That's true. If you say they all have the same conch, what you're actually saying there is A, B, C, and D have an equal concentration, which is not true because A could have a concentration of 10, B could be, I don't know, 4, C could be 7, D could be 2. So the concentrations don't have to be identical to each other. They just don't change over time. So just a little bit of like wording. They're unchanged or they remain constant, but be careful not to say they all have the same conch because that doesn't have to be true. Okay, so here's my answer. I said they would stay constant. That's what I said. Oh, for God's sake. Sorry about that, cut out for a second again there. Can you hear me again? This computer is like possessed by Satan. Excellent, okay, cool. All right, so next question then. If the position of equilibrium lies to the right, so that's where our imaginary line you'd push it to the right-hand side of the equilibria. What we mean by that, and this is probably the most important thing to get this terminology, if we say the position of equilibrium lies to the right, that means the forwards rate of reaction is faster than the backwards rate. That's what it means to say that the position of equilibrium lies to the right. So what would that do to the conch of A, B, C, and D? And can you think about each of those individually? Do you want to pop your answer in? Okay, when you're ready, guys, if you want to press enter. So we've got definitely a couple of different answers here. So let's have a think about this. By shifting the position of equilibrium to the right, you've meant that the forward reaction is now bigger. So can everybody type in this next question? If you have a forward reaction, just thinking about the forward reaction, what will that do to the concentration of C and D if I just had forward reaction? Will C and D increase or decrease in conch? Increase, right, excellent, increase. So if we shift the position of equilibrium to the right, what that means is you've made more forward reaction. So let's try that again. If we've made more forward reaction by shifting the position of equilibrium to the right, what will that do to the conchs of C and D? It'll increase, won't it? Okay, that's the answer. Excellent, nice one. So that's what we mean. So that's the most important thing to get in our head. If you shift the position of equilibrium to the right, you're going to make more products. So if we're in an industry, like let's say we're making some sulfuric acid or ethanol or whatever, you're going to want to make more products, aren't you? That's the point, because then you can sell it and get more money, basically. So usually what we want to do in industry is shift the position of equilibrium to the right to get more products. Occasionally, you might want to do the opposite. Let me just put my answer up. There we go, here's my answer. Occasionally, you might want to do the opposite and shift the position of equilibrium to the left. So last question on this page then, if we now shift the position of equilibrium to the left, so look, my imaginary line now lies to the left, what would that do to the conch of A, B, C, and D? Yeah, excellent, higher, excellent, Sam, exactly. Exactly, that would increase the reactants. And what would that do to the conch of the product? It would decrease them, wouldn't it? Because now you've got more backwards reaction. You've now made, I can't get rid of that first red arrow, but you've now made the backward reaction way bigger. This is the bigger one now. And so in industry, we don't usually want to shift the position to the left because that would make less products. Maybe if C and D was like toxic, you might want to shift the position to the left to stop it, killing everyone. But usually we want to shift it to the right. So here we go. concave A, B, C, and D. We'll do that. So let's go back to our first slide. I think we're ready to understand Le Chatelier's principle. Before I do that, does anybody have any questions about any of those terms or anything to do with equilibria? Yeah, I mean, technically, yes, but out of convention, we always say the products are on the right-hand side of the equilibria and the reactants are on the left. But that's just convention. Strictly speaking, yes, they are both products and both reactants, depending on whether you're thinking about the forward reaction or the backwards reaction. But we usually just say whatever's on the right, we're going to call that the products. Does that make sense? Yeah, cool. No other questions, guys? Looks like Theo might have one. Sorry, Theo. Can everybody else hear me? I'm guessing you can. Yeah, sorry, Theo. I don't know what to do about that. Apologies. Okay, so let's go back to our Le Chatelier's principle. So if you have a closed system, so basically nothing can get in and out, and it's in dynamic equilibrium, so the position of equilibrium's in the middle, then what will happen is if you change that, so if you change the temperature or pressure or anything like that, then the position of equilibrium will shift to minimize that change. So I'm going to sum this up in like a short sentence. Le Chatelier's principle says the position of equilibrium is not your friend. If you try and change something, it's going to try and stop you. So if you try and increase the temperature, the position of equilibrium is going to try and bring the temperature back down. If you try and decrease the pressure, the position of equilibrium is going to try and bring the pressure back up. Now, it never completely reverses what you've done. This word here, minimize, is important. It doesn't reverse the change, but it does minimize it. So if I change the pressure, if I increase the pressure by 100, the position of equilibrium would bring it down by, I don't know, 80 or whatever. Okay, so let's try and apply this principle to an actual idea then. So here's an equation. A plus 2b goes to C and D, and I've given you the enthalpy of this reaction. Now, the delta H given always refers to the forwards reaction. That's just a thing. It's always the forwards reaction. So a little quick question for you to type in. The fact that this delta H is negative, what does that tell me about the forwards reaction? You just bang out your answer when you've got it. Excellent, guys. Affirming you guys are in the know. Well done. All right, then. So if you could hold your answers back for this one. So type it in, but don't press enter yet. If I shift the position of equilibrium to the right, so my imaginary line is on this side now, what would that do to the temperature initially? Would it increase or decrease it, and why? I'd like a reason why. Give you a good minute or two to type in your answer for that, and then we'll all press enter together. So higher, is the forward reaction exo or endothermic? Okay, so I'm going to stop you there, guys. I think there's a bit of a misconception here. So when we shift the position, so if you can stop what you're typing, because we need to sort this out. So when we shift the position of equilibrium to the right, and you can just quickly type in your answer for this, are we making more forwards or backwards reaction when we shift the position to the right? Forwards, excellent. Is the forwards reaction exo or endothermic? Okay, exothermic. Does an exothermic reaction like a fire or a bomb increase or decrease the temperature? Right. So if I shift the position of equilibrium to the right, what will it do to the temperature? It will increase it. Yeah. Eureka moment there, Jason. Yeah, it'll increase it because you're making more forward reaction. And the forward reaction in this case is exothermic because the delta H is negative. Yeah, I'll pop up my answer. I'll show you what I said. I said, oh, bit of a bad spelling there, because you're making more exothermic reaction, which releases heat. That's why the answer will be increase. What do you think, guys? Does that make sense? No, it doesn't, Haya. You're misunderstanding it. That's not what the textbook says. So I'm not asking what direction the position will shift in. I'm saying it's a different question. But the question you're referring to in the textbook is not the question I asked. It's a different one. If you go back and read it later, you'll see it's asked something different. Okay, so exam question. If I wanted to make more C and D, think about Le Chatelier's principle. Whatever you do, the position of equilibrium will shift to reverse what you've done. Now, we're wanting to get the position to shift to the right, right, to get more products. So don't put in your answer yet, but you can type it in and get it ready. If I want to make more of C and D, we would say increase the yield of C and D. What should we do to the temperature? And explain your answer. So higher, I'll just go back to your thing. What the textbook says is if the forward reaction is exothermic, in order to shift the position to the right, you need to decrease the temp. So you just misread it a little bit there, which is fine. You know, we're all trying to pull through this together in weird circumstances. So it's not a problem. But yeah, that's not quite what it said. Okay, guys, when you're ready, if you want to press enter. We've got definitely two schools of thought here, haven't we? Okay, let's go through this. Definitely, again, this is not bad at all. So let's have a think about this. So I'm going to ask you some quick fire questions. You can just type in your answers into the chat box straight away. If you want to make more C and D, which direction do we need to shift the position of equilibrium? To the left or the right? To the right. So here's my arrow. We want to shift it to the right. So remember Le Chatelier's principle. Whatever you do, the position of equilibrium will shift to try and stop you. So if I was to decrease the temperature, so if I was to make the temperature lower, I'll just write that here. So I decrease the temp. If I was to decrease the temperature, what would the position of equilibrium try and do to the temperature if I decreased it? Would it try and decrease it further, or would it try and bring it back up again? Right, so if I decrease the temperature, the position of equilibrium will try and bring the temperature back up again. Which reaction increases the temperature back up again? The exothermic or the endothermic? Just bang your answers when you're ready. Endothermic reactions reduce the temperature. Endothermic reactions suck out the heat. Yeah, it's an exothermic. So think about a fire. A fire is an exothermic reaction. A fire increases the temperature, doesn't it? Yeah. So exothermic reactions increase the temperature. That's the bit we talked about up here, didn't we? Yeah, they increase the temperature. So if I was to decrease the temperature, then the position of equilibrium would try and bring the temperature back up again. And it would do that by shifting to the right to make more exothermic reaction. So the answer to the question is, if you want to make more of C and D for this equilibria, we need to decrease the temperature, as this will make the position of equilibrium shift to the right because the forward reaction is exothermic. And shifting the position of equilibrium to the right means more forward reaction. That's what that means. Whenever I say shift the position of equilibrium to the right, in your head, you need to think, oh, more forward reaction. So we're making more exothermic reaction. What do we think? Yes, no, maybe so? Okay, let's try two practice ones. So have a crack at just question number 1. So notice here that the delta H is positive. So you'll have to think about what that means about the forward reaction. And I want to increase the yield of C and D. What should I do to the temperature? Explain your answer. So the explanation is literally just stating whether the forward reaction is exo or endo. That is your explanation. Remember, whatever you do, the position of equilibrium is going to try and stop you. It does not like you. It is your nemesis. Hi, I'm not sure what you mean, sorry. Can I see the question? This is the question there. Yeah, cool, nice. Okay, people have stopped. Oh, oh. Maybe another bit more time. Okay, so do you want to bang in your answers then, please? Yeah, now we're getting it. Excellent, guys. Excellent. Yeah, yeah, yeah. Nice one. Nice one. Excellent. Excellent. Fantastic, guys. Yeah. Fantastic. So, as you've all said, because the delta H is positive, our forward reaction is endothermic, our backwards would be endo. And so, if we want to increase the yield of C and D, shift the position of equilibrium to the right, we would need to increase the temperature, because increasing the temperature will shift the position of equilibrium to the right as the forward reaction is endothermic. Excellent answers there, spot on. All right, let's try this question 2 then. Okay, when you're ready, guys, you want to bang in your answers? You guys are on it. And yeah, nice, nice, nice. Yeah, absolutely right. Yeah, spot on. So because the delta H is negative, that tells us the forward reaction is exothermic. And so if we want to shift the position of equilibrium to the right, we would need to decrease the temperature, because then the position of equilibrium is going to want to try and bring it up again by making more exothermic reaction. I'm really liking the fact that by your explanations, you're stating that the forward reaction is exothermic. That's definitely a good thing to do for your explanation. Excellent. Any questions? Sorry, a few more chats there. Yeah, excellent. Yeah, excellent. Yeah, nice one, guys. So any questions about that before we move on? Anything else you want me to clarify? No? Oh, good, cool. All right, then. So let's try one with pressure. Now, with the type of pressure we're talking about here, it's only moles of gas that matter. So imagine you're in a room and you breathe out. Your breath is going to expand, bounce off the walls, bounce off the ceiling, and it's going to cause pressure. If I'm in a room and I hold my phone in my hand, that's solid. It's not causing pressure against the walls, is it? It's not pushing against the walls unless I throw it at it, right? And if I had a glass of water, so a liquid, in my hand, that's not causing pressure against the walls or the ceiling. So when we're talking about pressure with equilibria, we only care about the moles of gas, because they're the only things that cause the type of pressure we're talking about. So my question to you, if I shift the position of equilibrium to the right, So again, here's our imaginary line. What will that do to the pressure and why? And if you could just hold back your answers for a sec, we'll all press enter together. Okay, when you're ready, guys, if you want to bang in your answers. Excellent. Yeah, yeah, yeah. Yeah, absolutely right. Yeah, here's what I would say. So, yes, it will. Can't use this computer, babes, anymore. It just cuts out all the time. Sorry about that. Cut out again there. Can you hear me again? Yeah, sorry about that. Yeah, absolutely right. So it will increase the pressure because if we look, that's kind of a circle. If we look on the left-hand side, there are 0 moles of gas. If we look on the right-hand side, there's 1 mole of gas. So there's more moles of gas on the right-hand side. So if you're shifting the position of equilibrium to the right and making more products, more forward reaction, you're going to make more moles of gas. So your explanation for why you shift, why you do anything with pressure is always talking about just state which side contains the most moles of gas. That's all we're going to need to do. All right, let's try a practice one then. So what should we do to the pressure for the above reaction to increase the yield of C and D? Explain your answer. Yeah, definitely. So can you explain the effect? Yeah, so basically when we're talking about causing pressure, only gases cause pressure of the type we're talking about. So if we're thinking about, let's look at this equation here on my board, A plus 2B goes to C and D. A, as far as we're concerned, does not cause pressure because it's a solid. B does not cause pressure because it's a solid. C does not cause pressure because it's a liquid. D will cause pressure because it's a gas. So if we're thinking about increasing or decreasing the pressure, making more products will increase the pressure because you've made more moles of gas. Yes, absolutely, Lauren. That's it. That's exactly the thing to get spot on. Yeah. That's what I meant, Lauren, when I said this sentence here. By saying shifting the position of equilibrium to the right increases the pressure, that is identical to me saying the forward reaction increases the pressure. Because remember, shifting the position of equilibrium to the right means making more forward reaction. So yeah, absolutely right, spot on. Okay, guys, if you want to bang in your answers then. Jason, you've talked about, yeah, you're really close, Jason. So you've talked about fewer molecules. Remember, we don't care about molecules. All we care about is moles of gas. So you have to think just about the moles of gas, ignore everything else. So do you want to have another crack at that? Want to change your answer? Same there, Daisy and Ina. Do you want to have another think about that? Oh, no, sorry, you're right. Sorry, Daisy and Ina, you're right. Absolutely right. Yep, apologies, Daisy and Ina, you are correct. And Sam, yep, you're right. Yep, spot on for you. Excellent. So we will decrease the pressure by, excellent, Laura, that's fantastic. By decreasing the pressure, the position of equilibrium is going to try and bring the pressure back up again. And it does that by shifting to the side with the most moles of gas, which in this equation is the right-hand side. Absolutely spot on. Nice. Let's try 2 more practice questions with that then. So here's practice question 1. So again, remember, it's only the moles of gas we care about. What should we do to the pressure to increase the yield of C and D? Explain your answer. Nice to have you back, Ina. Oh, she's gone again. Looks like your internet connection is almost as bad as mine, Ina. Okay, do you want to bang in your answers then, please? Excellent. Yep, nice one. Fantastic. Absolutely right. If we increase the pressure, the position of equilibrium is going to try and bring the pressure back down again, and it will do that by shifting to the right-hand side where there are less moles of gas. So our explanation would be we increase the pressure, so the position of equilibrium shifts to the right as there are less moles of gas on the right-hand side. Perfect. Let's just try one more practice with pressure then, and then we'll do catalysts and we'll call it there, I think. So last one then for pressure. Now be careful here, notice this word in bold. What should we do to decrease the yield of C and D? Explain your answer. So if we're decreasing the yield of C and D, think about which direction we're going to be shifting the position of equilibrium now. Okay, when you're ready, guys, you want to bang in your answers? Nice. Yeah, absolutely right. Well done. Absolutely right. Yeah, so we have 3 moles of gas on the left. We've only got 2 moles of gas on the right, so the left-hand side has more pressure associated with it. So if we want to decrease the yield, we're going to decrease the pressure to shift the position of equilibrium to the left, as there are more moles of gas on the left-hand side. Or you could have said less moles of gas on the right-hand side. That's also fine as well. Doing really well, guys. This is proper good. We'll just do one more thing then, and we'll call it a day, which is catalysts. So let's say we've got A plus B goes to C and D. So catalysts increase the rate of the forward reaction and the backwards reaction equally. That's just how catalysts work. So if I added a catalyst, what effect would it have on the position of equilibrium? Would it, in this reaction, would it shift to the left or the right? Yeah, you're on it, because it cancels out, doesn't it? So if you're increasing the forwards and the backwards by equal amounts, it ain't going to do anything. So catalysts are dead easy. They don't change the position. They do increase the rate of reaction. So they increase the forwards rate and the backwards rate. But because it's by an equal amount, those effects cancel out. You've done really, really well today, guys. Clearly, you've been really getting stuck into that workout set. So thank you for that. I know it's quite difficult to motivate yourself when you're at home and not coming in. So well done for managing that. Is there any last questions before we finish? Anything else anyone want me to go through? Oh yeah, Jason, every week. We're doing this every week, definitely. Yeah, for sure. Yes, please, Ted. If you just take some quick photos on your phone, it doesn't have to be anything like fancy. Just use your camera, quick photos, and if you send them on that that personal thread I've got with you on Teams, you can just like bulk send 10 pictures at a time. So probably you can get it all done in one lot. Just move in. Yes, if you shift the position of equilibrium in the exothermic direction, that will increase the temp, because exothermic reactions release heat, don't they? So that heats up the surroundings, and you're always measuring the temperature of the surroundings. That's what we say when we say temperature. Well, it'd be nice if we could get it by the end of the week, so by Sunday. Does that sound reasonable? Last pressure question. Yeah, so Daisy's asked to explain the last pressure question. So really quick go through this then. So we want to decrease the yield. So that means we want less C and D. So less C and D means more backwards reaction. So we're shifting the position to the left. Now, as there's more moles of gas on the left-hand side, to make the position shift to the left, we need to decrease the pressure. Because if you decrease the pressure, the position of equilibrium will try and bring the pressure back up again. And it does that by shifting to the side with more moles of gas. If they're ready and you're happy with them, brilliant, that sounds great. So well done. Just one last little thank you from me. You get a reward today for your lesson. You get to see, if it loads, oh, a picture of my dog. This is Tekken. He says hello. He actually says woof. So really well done, guys. If there's no more questions, we will call it there. Okay, it doesn't look like there's any more, so I'm calling it a day then. Thank you very much, guys. Have a good weekend. And yep, so I'll post in the chat about the one next week and like what it's going to be on and all of that kind of stuff. So do keep an eye on that chat we've got, that group chat. And yeah, same again next week.